Hi students, today we will see the concept of FPGA design flow by using Xilinx Vivado software. In this video, we are going to see the concepts of FPGA design flow with Nexys for DDR board. This is the board recently entered into the market, and with this board, we can do all the experiments which are given by the JNTUK or JNTUH or JNTU-IA. These are all the institutions defined laboratory experiments we can easily implement, and we can verify the synthesized outputs also. Okay, let us come into the topic. FPGA design flow with Nexys for DDR board we are implementing. In this first one, we will implement VHDL code, or we will develop VHDL code in the Xilinx Vivado platform, and we are simulating that VHDL code by using Xilinx Vivado simulator. And next, we are synthesizing the simulated program in the Xilinx Vivado by using Nexys 4 board. So these three operations we are going to see in this video. Let us start our discussion with the introduction of FPGA. First of all, FPGA design flow along with various steps are required in designing an FPGA from the very beginning to the stage where the design can be uploaded to the FPGA. The FPGA full form is Field Programmable Gate Array. So in the FPGA design flow process, here we have various steps. Okay, all these steps are required to designing an FPGA for a given digital system. So now we will start with the basics of FPGA. First, let us introduce FPGA technology very quickly. So this is the generalized FPGA architecture. In this architecture, we have CLB, configurable logic blocks, and memory elements, and digital signal processing part, and input and output terminals part. So these all are the different types of blocks are available in the FPGA. Other than this, we have some interconnecting wire mechanisms for programming the configurable logic blocks, memories, and digital signal processors. FPGA is a basically semiconductor device that comprises of logic blocks which are programmed to execute a specific set of functions. So whichever the functions we are giving by using a high level language, those all functions will be converted into machine level or binary language, and with this binary level language we are operating all the blocks are available which are in the FPGA architecture, like configurable logic blocks, memory, and digital signal processing blocks. These programmable logic blocks are connected to each other with the help of an interconnect matrix. Here, the interconnect matrix we are representing with the hash color lines. So these are the hash color lines which are used for interconnecting these logic blocks. These logic blocks to DSP, and these logic blocks to memory, and these logic blocks to input-output connections. These all are the connections we are making here. So CLB to input-output block, the CLB to DSP block. Say one CLB to another CLB, and one CLB to memory element. So these are the different types of programmable interconnections are available in the matrix format. Next, these interconnects are responsible for connecting the logic blocks and facilitating the flow of signals across the chip. So whenever you want to implement a digital system, you require more number of logic blocks and more number of memory elements. These interconnections forms grouply, and they will connect all the logic blocks from one place to another place, or memory blocks from one place to another place, and they will implement our required digital system functionality. these signals will easily transmit through using this interconnecting wires. The structure is arranged in the form of a two-dimensional array consisting of logic blocks, interconnects, and input-output blocks that connect it with the input and output signals. Let us continue the FPGA introduction. These are the last two important points we have to remember. Is mandatory when you are designing FPGA architecture. A logic block itself, it is comprised of a lookup table, or we are calling generally LUT, and a flip-flop or FF, and a multiplexer. So in this configurable logic block, whichever the configurable logic block we are representing, in this configurable logic block, we have some lookup tables and some flip-flops or some multiplexers. So in this CLB, we have three different types of elements. We have lookup tables called LUT, and flip-flops, basic memory storage element devices. Flip-flops, we are generally representing FF, and we have some multiplexer for selecting the data. So these three elements are we have in the configurable logic blocks. So this is the short introduction of FPGA. Now coming to the benefits of FPGA. One of the major benefits of using FPGAs is that they are reprogrammable. That means when you have written the program, you can erase the program and you can reprogram again. So that means you can execute multiple number of programs. You can implement multiple designs in the same FPGA. Okay, so this is the very most important and more important benefit, meaning they can be modified to serve a function that is completely different from the one they are performing before every time the designer uploads a new code to FPGA. That means if you are completed dumping your written code into the FPGA hardware, so you can change the program and you can again upload or dump your program into the hardware. So you can do this operation multiple number of times up to getting your required functionality. That is a very important and very attractive advantage with the FPGA. Next, coming to the steps involved in the FPGA design flow are 5 major steps. The first one, design source files. Designing of source files, that is the first one. Second one, simulation. So the design of source files, here we are designing the source files by using VHDL language or Verilog language, where VHDL stands for we have VHSIC HDL. We can also call VHDL as VHSI HDL, where VHSI HDL is nothing but as very high speed integrated circuits hardware description language. Here HDL stands for hardware description language. VHDL stands for VHSIC HDL, where VHSIC is nothing but as very high speed integrated circuits hardware description language. So by using VHDL language, we are designing the source files. After designing the source files, we are simulating that VHDL based design source files. So after simulation, we will get the simulation results. With this simulation results, we can verify our digital system functionality. If the simulation results are satisfied with our requirements, then we have to start the synthesizing the process. Before going to synthesize, the second step is input-output constraints. Let us see the first step. We have to design the source files by using VHDL or Verilog HDL. First one VHDL, second one Verilog HDL. Here, the second one is a schematic entry. We can write the hardware description language by using two languages, and not only by writing the code, we can design schematic entries. That means we can drag and drop the different types of predefined blocks. With that also, we can design the source files. So after designing over the source files, we can start implementing the functional verification. This is the one very most and important parameter to verify the functionality of our digital systems by using different types of simulators. In this video, we are using the digital simulators as Xilinx Vivado software. This is the first step. And second step, we are implementing the input output constraints. That means we are mapping the hardware input output pins with the our software defined input output functions. If you are writing in your program, A and B are the input pins and Y is the output pin, these input and output pins we can map to the hardware. That is the second step. And third step, design, synthesis and implementation. Here in this synthesis part, what we are doing, we are converting the program or the high level language code into the synthesis, into the gate level netlist file, where the synthesis process converting high level language code into the gate level netlist file. That is the very important. And coming to the implementation process, we are placing all the gate level netlist file contents into the right places of the configurable logic blocks of the FPGA, and we're making the routing in between the CLBs based on our design. And finally, we can identify the optimum routing, optimum placing, and optimum utilization of input and output terminals by using this implementation process. And next step, bit stream file generation. This bit stream file, which is used to dump or upload into the target hardware device, that is Nexys 4 device. So once this bit stream file is generated, now your program is ready to upload into the next step, that is FPGA board. So this is the FPGA board here we are using. This is the FPGA board we are using, that is Nexys 4 DDR board. We can implement, we can dump or upload our code into this hardware. Let us see all these steps one by one easily, right? So here coming to now, I am opening Xilinx Vivado 2016.1. So the software is opening very slowly because of it has a lot of libraries, predefined hardware libraries are available. So for that reason, it will take some time to open. So I have installed this Xilinx Vivado 2016.1 version. First, create new project. Here you can see quick start, tasks, information center, and here you can see the recent projects options also. These are the recent projects I have completed previously. Now start with the new creation of new project. Create new project. Click on this create new project. Then you will get a pop-up window. So create your new project. In this wizard, you are selecting first your project title. So this is the sample project I am creating here. Sample project _2 I'm creating here. Click on the next. In this, you have to select RTL project. This is the RTL project which is used for the generating IP and running the RTL analysis, synthesis, implementation, designing, planning. That is our FPGA design flow we can do by using this RTL project. So select this RTL project, then click on next. So here you have to add or create your source files, right? If you are already written your code in the some notepad files, you can call all these files to here by using add files option. Otherwise, you have to create whatever the files you required here. Okay, so we can add these source files after creation of the project also. So for that reason, I'm not selecting any add files and create file operation. Then I'm clicking the next button. In the same way, IP protocols also, here we are not adding any IP protocols. So I'm clicking the next here. I'm not adding any constraint files here, that we will see step by step wherever you required. At that place, we will add. So here I'm also clicking on the next. Now here we have to select our target FPGA hardware board. So here I'm using target FPGA board as Nexys 4 board, which I have shown in this PPT. So see here, this is the board I'm using. This is the board is consisting of RTX 7 and general purpose board. So these options we have to select in the default part option. So see here, this is the default part option. First, product category, general purpose, and family RTX 7. Here we have to select. So here we have to select RTX 7, and package here we have to select CSG 324, and speed grade you can select any one of the speed here. For example, I am selecting -3. So this is the hardware board we have to select. So here I have selected product category as general purpose, family as RTX 7, package as CSG 324, and speed grade I am selected -3. Finally, this is the board I am selecting XC7, that is RTX 7 A 100T CSG 324. CSG 324 is the our target board, and speed here it is the -3. This board I am selecting, and I am clicking on the next. And this is the summary, whatever the project we are creating, the new project summary. Default part is XC7A 100 TCSG 324 -3, and product RTX 7, family RTX 7, package CSG 324, speed grade -3. So this is give the summary sheet. Then click on finish. So after clicking the finish, our project is going to open now. So these are the different types of windows are available in the new project. So see here, the first one, Flow Navigator. The left side topmost one is the Flow Navigator. Here we can see the Flow Navigator. Here we have the Flow Navigator button. I am representing it with the red color tick mark. See here, this is the Flow Navigator window. Next, this is the Project Manager. This is the Project Manager. Under the Project Manager, we have sources and properties. We have sources. Whatever the sources we are creating, a new VHDL file creation or new test bench creation, all the files we can see in this area. We can see in this area. And coming to these files properties, we can edit the properties of the files in this place. Next, in this location, we can see our project summary. Otherwise, when we are created a new file, those file behaviors or details we can see. That means we can write the VHDL code at this part that we will see later. And when the design is going to run, we can see all the parameters here. Okay, the properties are it is the console. Otherwise, it will generate different types of reports, and it will show a lot of important parameters which is we required when we are implementing this process. Okay, these are the different types of tabs are available. In the Flow Navigator, here we have the Project Manager first one. By using Project Manager, we can add or remove all the sources. Then after completion of writing the VHDL code, we have to simulate here, and next we have to do RTL analysis. Next we have to do synthesis process. Then we have to start implementation part, and next we have to complete program and debugging operation. Also here we have to complete programming and debugging operation. So the last one is the Open Hardware Manager. Before Hardware Manager, we have to complete our process up to generation of bit stream. This is the final step before uploading or downloading the hardware into the target device. So these are the all steps here we have. We will see one by one step easily, step by step. Right. In the design sources, you have to give the right click on the design sources. You have to give the right click and click on the add sources option. on the design sources, you have to give right click on add sources, add or create design sources here. Then click on next. Here we have the remaining options also, constraint files, adding, simulation sources, adding, or DSP sources. These all are not required presently. We have to first create, add or create design sources. Then click on next. Here we have to see creating a file. This is the window already we have seen when we are creating project. So I have not explained these details previously. Now I'm going to show how to create a file. So see here, I'm creating a file. I have clicked on the create file. So file type VHDL or Verilog. Here I want to write my code in the VHDL language. Now coming to the file name. Here I'm creating some file name. For example, logic gates I want to do. So logic gates, total 7 gates are available. So I'm writing logic gates 7 and click on OK. Now see here, my file is created here. You can see I have written the logic gates 7. So the file is with the extension of .vhd. And here are the library details, location, all the details are available. Now click on the finish. So after click on the finish, it is asking what are the input and output ports are going to design in your VHDL language, VHDL file on your the required system. Now click on here port name A. This is the input port, and click here B. This is also input port. Now I want to implement all the logic gates by using this Xilinx Vivado. So for that reason, I'm writing all NOT gates. For example, NOT G. I'm writing NOT G. This is one output file. Here I'm selecting the direction as out. When I'm selecting input A, the direction of the input is in, that is input. It is already available default. So for that reason, I have not changed. Here I'm writing output. Output is I'm representing one variable name is NOT G. That is the output direction. I'm representing that is not in direction, out direction. Next, and G. This is one more output. This is also I'm changing as out direction. Next, RG, this is out direction, and NAND G, this is also out direction, and NOR G, output terminal, XOR G, X NOR G. So these all are the outputs. Okay, totally 3 input ports and 7 output ports I have written here. Then click on OK. Now, so under see here under design sources, one file is created, logic gates 7. Now double click on this one. You will get one file here, logic gates 7.vhd. This is the file now created. So see here, this is the very small area. We cannot see the complete window, the complete program here. So for that reason, here we have 3 buttons. One is close button, and one more is here we can see the pull out button, and one more is the maximize button. First click on the pull out button. This window will come to out. The window is coming out, and click on the maximize button. Now you will get the full screen window. So this is a full screen window. In this full screen window, you can type your program easily. And coming to the first one here, these are the comment lines which are representing in this color that is very light black color. That is one type of gray color. So these are the details are not required for us when it is created like this is available. And coming to here, the first one, header files, library, IEEE, use IEEE, std_logic, all these files are available. First, we have to write the header files like this. Next, the VHDL program is divided into 2 parts. The first one, entity declaration. Second one, architecture declaration. In the entity declaration, what we are doing here, we are writing the what are the input ports or output ports are available. These all input and output ports are we are defining with the entity part. So see here. First, I am writing entity name is. Here, the entity name I am writing as logic gates 7. My file name only, here I am writing as entity name. So this is the automatically program came from the Xilinx automatic project creation process. Okay, the entity word, if you see clearly, it is a keyword. Entity is a keyword. So for that reason, the color of entity word is we can see with the purple color, and the now file names are entity names. These are the user defined names. So you can see these file names are with black color. Okay, entity name is. Now we have to start declaring the ports. So the ports, we have to write the port and open the bracket. So A is the in. A is the in type direction, that is input type. It is std underscore logic data type. It is the std underscore logic, that is standard logic data type input port here we have. Okay, right. So B also input type, and it is also standard logic type data type input terminal. And now coming to the output terminals, not G, output direction and standard logic. Like that, each port we are declaring, we are writing semicolon. B we have defined, right, written on the semicolon at the end of the data type. And next coming to that, not G, out std underscore logic, we are ended with semicolon. Like that, each and every port we are defining and we are writing a semicolon. So see, except last port, so the last port we are defined, and we have used the port braces. So whatever the braces is available here, the same braces opened at the starting of the port. So these complete ports we are closing at the last port name without mentioning any semicolon. So after closing this braces, we are representing the semicolon. Okay, this is about the ports declaration. Now, end entity name. Here we have to write end entity name for closing the entity part. There is no need of writing end entity. We have to write end entity name. That is a very important one. Right. So this is the entity declaration. Now coming to that architecture declaration. So architecture declaration also, architecture is the keyword, architecture, and this is the architecture model. This is called architecture model or architecture name. Here default it is came behavioral. Now I am changing this is as data flow. Okay, if here I'm written architecture name as data flow, at the place of ending of the architecture name also we have to write data flow. Otherwise it is showing with red color underline. So if it is showing a red color underline, there is a mistake in this instruction. Okay, so for that reason here we have to change. Here we have to write end architecture name. The architecture name is data flow. This is the our architecture name. If you written the same architecture name at the declaration of architecture, and when you are ending the architecture, the same name written, then there is no error we can see here. Now coming to start writing the code. So I'm writing here the data flow style. First I'm writing not G, and we have to write equal to symbol like this, less than equal to. This is the assigning operator. This is the left assigning operator, and we have right assigning operators also that we have to see from the VHDL tutorial. Okay, so first one, not G output, not G is equal to, not G is equal to, we have to write like this, not of A. Here not gate operation we can write for only one input. So the output variable is not G and the function is not A. After performing the not A operation, the output is assigned to the not G output variable. Next, in the same way, and G. Here again you have to assign A and B. Right. So for the A and B input variables, we are operating the we are using the AND gate operation, like RG is assigned A or B, like NAND G, A, NAND B. Next, NOR G, NOR B. Next, XOR G is assigned A, XOR B, XNOR G, A, XNOR B. Here we have taken XOR G, XNOR B. EX we have not taken, right? So these are the architecture we have written in the data flow style for the logic gates. Now pull in to this button. So the code is are fixed here, right? The window is fixed here. Now coming to here, so we have to save. So see, you have to use the save button here, right? I have saved this program. Now I have to simulate this file. So click on this run simulation button. Then it will come. Then it will show run behavioral simulation. Then click on this run behavioral simulation. So after clicking here, you will get different windows. So after execution of the simulation, you will get 3 windows. So this is actually previously source window. Now see here, this is the source window. Beside of the source window, one scope window also came. Beside this is our scopes window, we have the object window, and here we have untitled window. This untitled window, it is nothing but as a waveform viewer. Now we have to give the inputs for A and B. What is A, what is B? Here we have to give. Then we will see what is the output behavior. So give the right click on A and give the force constant. Here I'm giving the A value is equal to 0. Here force value I have given 0. Okay, then click on OK. Like that. B also you have to give force constant and click give the value of 0. Right, A value is 0, B value 0. Now simulate this one, that is run. F3 button is the shortcut button, otherwise you have to click this button, run button. So see here, if A is equal to 0, B is equal to 0, not gate operation, not is equal, not gate operation, not G is equal to not of A. That is, if A is equal to 0, not gate output is 1. AND gate operation, if both inputs are 0, 0, output is 0. OR gate operation, if both inputs are 0, 0, OR gate output is 0. Like that, you can verify all the logic gates operation. So the remaining combinations of inputs, A is equal to 0, B is equal to 0, we have given now. Now the remaining combination, A is equal to 0, you have to give, and B is equal to 1. Right click here, B on B, give the force constant, click on 1, and click OK. Now A is equal to 0, B is equal to 1. Click on OK here. Now based on the 0, 1 combinations, you will get the outputs here. Okay. So like this, you have to check each test case of the A and B input values. You can verify your truth tables of logic gates here. Okay, right. So this is one way of verifying the outputs. Another way of verifying the outputs by using graphically, that is in the place of A, give the right click and give the force clock. This is another way of observing the outputs by using waveforms. So here in this force clock, we have different types of options: leading edge, trailing edge, duty cycle, period, offset time, starting of the offset, cancel of the offset. All these are options are available. So here click leading edge is 0, trailing edge is 1. Keep the duty cycle as 50% and period is 100 nanoseconds. Keep this one for input A. Okay. For the B signal, you have to keep leading edge 0, trailing edge 1, and period you have to reduce half for 50 nanoseconds. Why we are applying that, we will see after executing. Okay, I have clicked on OK. Now click on B, give the force clock, leading edge again 0, trailing edge is 1, and here you have to put 50 nanoseconds. Why I have kept 50 nanoseconds? Now I will show. Click on OK. Okay, now run this values, whatever the force clock we have given for AB. Click here, run, and here you have to break operation again. So cancel here, and you have to pause this operation. Now, so something output we got here. Now we have to see this output clearly. So first you have to float or pull out. So I made float, that means I have dragged out. Now I'm doing maximize button here. I have used maximize button. Now what I'm doing, see here, zoom in, zoom out, and zoom fit. 3 options are available. Now I am first making zoom fit. Okay, this is a zoom fit option. Now I am clicking somewhere in this waveforms. Here I have clicked here. So when I'm clicking here, some yellow color line came. So at this place I am zooming now. Okay, now Right. Now see here, I'm zooming here. I'm zooming. So see here, I'm zooming. Now the waveforms are visible clearly now. See here. So from here to here, right? From here to here, I again zoom. Go to just zoom out. Okay, right. So see here. Some I want to add markers. So here markers are not available. Okay, no problem. So see here. So this is the A signal. This is the A signal. At the place here, so see here, from here, the value of A is equal to up to here it is 0. Then up to here it is 0. This is for A. Okay, from here to here A. Here also A is there. This complete line is A. Here A value is 0, 0. Here I'm representing. So see here. At this place 0, A value. Here the A value is 0, here the A value is 0, here the A value is 1. And here the B value is 0, B value is 1, and here B value is 0, and B value is 1. Here the combinations first AB, if you take here it is 0, 0. If it is here, if you take here 0, this is 0, 1. If you take here, it is 1, 0, and it is 1, 1. Okay, here why I have taken first A, the time period is 100 nanoseconds for A and 50 nanoseconds for B is, here I want to repeat all the combinations of inputs. That is 0, 0 is one combination, 0, 1 is another combination, 1, 0 is another combination, and 1, 1 is the final combination. For all these combination, I got all the outputs here. Okay, so see here, when I'm using this yellow color line button from here to here, I'm dragging. When I kept here this yellow color line here, at the place of this location, the input value is equal to A is equal to 0, B is equal to 0, and these are the output behaviors. And now move from here to here, this yellow line. Okay, now move this yellow color line from here to here. Now at this place, A is equal to 1, B is equal to 0, and these are the behaviors of the outputs. Like we have to see all the simulation results with your truth tables. You have to verify the output functionalities. Okay, if you want to take printout, you can take printout by using print screen button. Okay, then you can put in your observations or records. Otherwise, for further purpose, you can use. Okay, with this, we have completed the simulation part. In the next video, we will see the synthesis part with the Nexys 4 DDR board. So this is the first part 1 video, and part 2 video, we can see the synthesizer operation. Okay, thank you.